bit input, the 8-bit input right there, and then the output of our logic diagram. The first 2 bits are for the tens, I mean for the hundreds digit. The next 4 bits are for the tens digit, and the last 4 bits are for the ones digit. So how this algorithm works is that there is a series of conditional adders, and at every instance of the conditional and oh, can you go back to the big block diagram?
Oh my bad. Do you want me to zoom in here? I
So
was just gonna show like that.
yeah, oh, no, like right there, yeah, just so like um, so as we can see, every one of those big blocks are a conditional adder, and what happens is a 4-bit input enters the conditional adder. If that value is greater than 4, then the 4-bit value is +3, and it outputs. And if not, then the normal 4-bit value just passes through. If you can zoom out. So since this is a purely combinational design, the next 4 bits, the next 4 bits to the right are enter the next conditional adder. So that's how the double double algorithm works. Now Aman will talk about our methodology for designing the circuit.
So initially we started out with the D flip-flop design in multisim. That didn't work, not even in multisim. So we came to this combinational version, assuming that in multisim timing is already that difficult. We're not going to try to do timing in this right here. So we did some math, and this is the most efficient output without the use of timing, even though it's pretty large. It can be much faster, but of course we have just implemented it in electric. We used LT Spice to simulate it. So taking a look at some of the gates we have up there, we have an AND, we have a comparison inverter, we have a MUX, NAND, OR, top, and XOR. The 4-bit adder is a combination of the comparison and the MUX, if you can go to that one right there. The top one, I mean, sorry.
Over here.
Yeah, that's fine, you can zoom in.
Oh, okay.
So those at the bottom are muxes. They take in an input or take in 2 inputs and output only 1 output. And those are controlled by the comparator to the far right side. That's just one small module right there. And the adder is right above it. Now those 4 input lines that are blue up there, if you can highlight them. Right there, those are the input lines. And then the output lines are, well, that's the output for the adder. And below that is the output for the conditional add. So that will add 3 or add 0 depending on if it's greater than or equal to 4. Anything else?
Okay. Do you want me to start the simulation now?
Oh yeah, you can start simulation.
This is a simulation. So the way that simulation works is that.
The one thing I forgot to say, electric VLSI does not like simulations. Yeah, so we went at least twice. Yeah, you can carry on now.
Okay. So this is our inputs right here. So we're inputting our values here from 0 to 7, and our value should read as 1 volt right here as we have our VDD. So our VDD is basically what we're measuring from our PMOS to our ground whenever we have a value of 1. So if I run this simulation on LT Spice, this is what we get. So we inputted high for every value. So the input for every value is high. It's really hard to tell because LT Spice it gives everything out in the most the convenient way possible for itself. So sometimes the outputs can be inputs can be random, but the outputs in this situation actually were able to be in order, so it's a little convenient. So from the least significant bit, which is this one, to the most significant bit is this one. So if we're going from the first single bit, we have 1010, which is 5, and then for the next digit, we have 1010, again is 5, and then we have 0, 1, which is 2, which is 255, which is the correct value if we input all 8-bit values as a high, which would be 255 in binary.
We can still talk about some of the gates. I mean, If you're watching this video, you probably already know how to make them or have made them already. Can you open up the NAND layout specifically? Yeah, our PMOSs are 3 times bigger than our NMOSs, and I forget the unit size that we used for the NMOS PMOS. If you could double click one of them. 5 by 15. Okay, yeah,
Let's say.
that's what we used.
Oh, yeah, yeah.
But yeah, if you can click on one of the schematics, that's one thing.
These all do pass the DRC check.
Right.
The
They also
DRC
do
check,
the NCC check, which is comparison between layout and schematic.
and they do pass it. We can do size checking as well, but we were not trained in that aspect, so we can't give anything correct or be assured of anything that's correct.
And last thing we want to mention, electric VLSI does not like XOR gates either. If you want to open up the XOR gate, either schematic or layout, but yeah, it's made of NANDs. We made one that was non-CMOS. It worked temporarily, but LT Spice doesn't like non-CMOSs, so we made it with NANDs. Of course, everything else could be made with NANDs, but this is the one that gave us the most issues, so we decided to just go the easy route.
This is correct. Yeah, this is the only one that gave us correct values, so
Yeah.
we can't use anything else.